All right, so in this one, we have a wind is blowing at 45 miles per hour. The wind is blowing in a direction 30 degrees south of west. Find the westward and southward components of the wind. We're mostly concerned with south and west, so I'm going to draw south and west here. North and east we don't need to be too worried about. So it's blowing in a direction 30 degrees south of west. So when we read that, west is our main direction. That's the side we're actually going to touch with our angle. And we'll go 30 degrees to the south of that. So that 30 degrees will be here. And the speed at which that wind is blowing is our magnitude, so that's 45 miles per hour. So we need to find the westward and the southward components of the wind. So this wind is blowing in this direction, but it would have a westward and a southward component. I'm going to call this side W, and I'm going to call this side S, although S is a terrible variable. So it's like 5. For most problems, when I do vectors, I use the parallelogram method whenever it introduces you. I used to do the triangle method a lot more. So whenever it introduced that to you, it showed you those two different ways that you could do that. I used to do triangle a lot more, but I found students do a lot better with parallelogram in general. Now, if you like doing the triangle method better, that's fine. If you like doing the triangle method, then that means instead of drawing this southward component right here, you might would have drawn it right here, which is fine because obviously those two sides are the same, right? Same length. This, of course, would be important if you are looking at a force upon an object. It could be wind. So if you had a wind blowing against, say, a south, like if you had a, westward facing wall right here, that westward component is the component that's really putting that pressure against the wall if you're worried about it like caving in, right? So you would, whenever you look at strengths of things that you would be designing, you would consider that westward component and what that would need to be here. So there are times where you would need to break down west and south components. So if we're breaking this down, we're going to find south or west first. It doesn't matter which one we choose here. So I'm going to go for the west side first. Now, south and west are perpendicular to each other. So these are right triangles that we see here in this picture. And I know this angle right here is 30. I know the hypotenuse is 45. So if I'm going to look for that west side right there, I need to use trig to set this up. So this side right here, west would be my adjacent side, and 45 would be my hypotenuse. Summer, which one am I going to use if I've got adjacent and hypotenuse? Cosine. So we will do cosine of 30 degrees equals adjacent, which is our W, over hypotenuse, which is 45. And then we just have to multiply both sides by 45. So 45 cosine of 30 is going to give us 38.971. So our westward component here would be 38.971 miles per hour. another thing to keep in mind here, think about when you set it for south, should south be more or less than 38? Assume I've got it like a little bit to scale anyway. It should be less because this length right here is shorter than the length of this side right here. So I would do this time, instead of doing cosine, if I want south, I need to do opposite over hypotenuse. So Blaine, which one do I use when I have opposite and hypotenuse? Sine. So we'll do sine of 30 this time. Is south over 45. We'll just have to multiply both sides by 45 to solve that. So 45 sine 30 is going to give us 22.5, which I should have known without. So you would have a southward component of 22.5 and a westward component of 38.971. You could, yes. On last step, you could use Pythagorean theorem if you would rather. The only thing I would caution you on Pythagorean theorem is make sure you use that answer button, so you're using that whole decimal. Don't round the 38.971 off. It'll throw S off a little bit if you do that. But yes, if you want to use Pythagorean theorem instead, you could, because you've already got two sides of that triangle. Good. Okay. Another good thing about using the variables W and S is if you do this on the test, I can't remember. No, this test. Let me look real quick. Let me look. I can't remember if this test is online or on paper. Okay, it won't be terribly important because this one's online. But whenever you're doing this on paper, if you use W and S, it will help you. You wouldn't have to state west and south. Also, even if it's not on paper, this is a good idea because probably if it's online, it's only going to ask you for one of those answers, not for both. So that makes it clear that you've got the right one. Okay, I'm sure it would be way more complicated with this, but I'm reading a book right now that's very interesting. It's called The Devil in the White City, and it's about the World Fair in Chicago in 1893, and I did not know this, but that was where the first Ferris wheel was erected there, and the first Ferris wheel, and it's called Ferris because the guy that designed it, they had like this competition for people to design something grand for like the main part of the fair. The first Ferris wheel was like 260 some feet tall, and it had cars that held 60 people a piece, so it was like 2,000 people on the whole Ferris wheel at one time, and like they had never built a small Ferris wheel before that I know of. I mean, they might have tested something, I don't know, but in the book it doesn't make it seem like it. Anyway, and Chicago is a windy place, and I think something's going to go wrong soon based on the title of the next chapter, but I'm not there yet, so I don't know. And I keep wanting to just Google it and see what all happened, but but I've not yet, just because the book's better if I do that. It's also about a serial killer. It's not a happy book, but it's really interesting. But certainly, lots of calculations go into things like that. Whenever you're building, like a skyscraper or something, if you're building a skyscraper, those things like actually like sort of move a little bit. Like the wind can have a big impact. You don't need to build something that magnitude where wind is going to be a big factor. I know when my husband was in school, I can't remember which class, statics, dynamics. Statics definitely had a lot to do with it, but the wind would be moving, so I'm not sure. But even things like whenever you're driving down the road and there's a big pole and those great big signs over the road telling you you need to be in this lane or exit's coming up, you know. The small ones on the side of the road, maybe not so much, but I'm talking like these big ones that go out over the road. Wind is a huge factor for those because they're basically just, you know, like a big flat surface of thin metal that's not very heavy. So it catches a lot of wind, and certainly you don't want those things toppling, especially the ones that over the top of the road. So there's a good bit of calculations that go into just making sure that those forces are balanced, that they can withstand the wind, and all sorts of things like that. My husband's roommate in college, he designed cell phone towers. He works in Raleigh and works for a company that designs cell phone towers, which I also did not know this about cell phone towers. Not all of them. Some of them are just a little tall. But, like, there are lots of cell phone towers that are, like, taller than the tallest skyscraper. And so they have to have lots, and, well, really all of them, but especially those super tall ones have to have lots of engineering that go into them to make sure that those are not going to just fall over, because that would be not good. Not as bad as a building full of people falling over, or a Ferris wheel with 2,000 people on it falling over. I haven't Googled it. If you Google it to see what happened, it seems, I'm hoping it's a minor accident. If you Google it, don't tell me. I need to read the book first. I feel like if it was a major accident, I would have heard it before. But I don't know. Maybe not. There's a lot of things about this book as I'm reading it. I'm thinking, how did I not already know about this? So, it's interesting stuff. Alright, so this time we got a sled. The sled is being pulled with a string. The string makes a 62-degree angle with the ground. The person pulling the sled is exerting a force of 4 newtons. What are the horizontal and vertical components of the force? So in this case, we've got our sled over here, and we've got a rope tied to the front of the sled, and we've got a person over here. Stick figure looks weird with their arms down, doesn't it? And they are pulling the sled along. We are going to assume flat ground here. I should have said flat ground. And we're pulling it in this direction. So, although I might not want to put that arrow there because it might mess up our vector here. So, this string, if you think about this here, the force as you pull on that string is pulling the sled with a vector in this direction. So our force is 4 newtons. We use a capital N for that. But whenever you pull upon that string, what you really have there is you've got 2 forces, right? One of those forces is pulling this to the right. The other part is pulling it up, right? Because it's going up and to the right or forward in this direction. So if you make a parallelogram there, my vector's basically already drawn because it is my string. So whenever you pull, in this case, the only part that's actually doing the work that you want it to do is the work that is pulling the sled along the ground, right? So it would be much more efficient here if we were pulling this rope flat with the ground. But the problem with that is to do that, you would have to get on the ground and crawl pretty much, right? Or have super long arms or bend way over. It would not be very comfortable. So you would more than likely pull the rope like we see here, right? But it is pulling up on that sled, and depending on what type of sled you have and how long your rope is, it may even like lift the front of the sled up off of the ground some. This is sort of wasted force right here, right, that you don't really need. So we can calculate those forces here, and we can tell how much of this work is actually helping and how much of it is that like upward sort of wasted force. So I'm going to call this side right here, I'm just going to call it X since it's horizontal, and I'm going to call this part right here Y since it's vertical. And the picture's not to scale very good here. I should have done that a little bit better. That should be a 62-degree angle, even though it looks like more like a 30-degree angle there. So if I want to know the horizontal force, this is my adjacent, and here I have my hypotenuse. So I would do cosine of 62 degrees equals X over 4, and I would multiply both sides by 4. And so X would be 1.877 or 879 if I round it to 3 places. Newtons. That's our horizontal force. And then if I want to find that vertical force, I've drawn my vertical force over here, but it really is the same as this side right here, so I could call it Y right there. Hallie, how would we set it up for that one to find Y? Perfect. And all we have to do to solve that one is multiply both sides by 4. And we've got Y is going to equal 3.532 newtons. That's our vertical force. So certainly this person is using a lot more force upward than they are forward. So, to fix that, they could adjust some things. Basically, this angle right here, you would like for it to be smaller. So they could either hold their hand lower, which might help, or if their string was longer, then they could have a lower angle there. That would give them a more effective, more efficient use of their force to pull the sled up the hill. Again, if you got a little plastic sled, this is probably not all that important to you because it's a very tiny amount of force anyway. And certainly if you are pulling a sled up the hill, snow sledding, you probably don't, you're probably not going to go calculate this, but you can see how this would possibly apply to other things that you would be concerned with in lots of different areas. So those angles could make a big difference, certainly in designs for really probably lots of things, manufacturing sort of things, possibly lots of different places where this sort of stuff could apply. Okay, this is just like scratching the surface of vectors. I know somebody that I talked to, somebody a couple years ago had said that they had taken the NCCSM class on biomedical something or another. Yeah, and they used vectors for like looking at forces on like a knee or a hip for like doing knee replacements or hip replacements and making calculations on angles there. So so there's lots and lots of applications for this stuff. We're sort of just scratching the surface. Huh? Really? I can't remember who it was that was telling me about that one. It's been a couple years ago, though. It was probably pre-COVID. There. All right, so this is just what I sometimes call a naked problem here. It's not got any application at all directly, but it's just sort of a practice problem for us to see what's happening. So vector A has a magnitude of 3 centimeters and a direction of 0 degrees. Vector B has a magnitude of 4 centimeters and a direction of 50 degrees. We are supposed to find the magnitude and direction of A plus B. So we got 0 and 50 degrees, so we're looking in the first quadrant here. And vector A has a magnitude of 3 and a direction of 0 degrees. So I'm going to draw it here. 0 degrees is just along that x-axis there. 50 degrees, when it just gives an angle like this, like you don't have a north, south, east, or west, it just gives 50 degrees. They're intending for you to start at 0 degrees and go counterclockwise that many degrees. So it could be anywhere from 0 all the way to 360 degrees, which would be rotating all the way around. We're at 50 degrees here, so this vector will look something like this, and I'm going to try to draw that a little bit longer than my other vector. This angle right here will be 50 degrees. Right now, I'm not going to make you draw these to scale. Tomorrow, when we do some, we are going to actually get out the protractors and rulers and draw them to scale, just because if they're not drawn to scale, sometimes it makes it really difficult to do the problem. So another thing that I want to make sure that you are doing, when you draw these, please, please, please draw the endpoints as dots and the ends as arrows. Okay, so for vectors, the endpoint is a dot and the other is an arrow. This looks like what we would call a ray whenever you're dealing with geometry, and that arrow means that that goes on forever. With vectors, it does not mean that that line goes on forever. It means we're going in this direction. So it means we started from here and we're going in this direction, but we still stop our length. So this was 4 centimeters, and this one right here is 3 centimeters. All right, so I'm, in pretty much all cases, going to teach you the parallelogram method, just because I have found that most students seem to do a little better with that. So, to add vectors together, we are going to make a parallelogram. Thus far, that parallelogram has been a rectangle because we've been dealing with 90-degree angles. But it's not going to be for this problem. So, I'm going to use a dotted line here. And I'm going to just extend this dotted line out parallel to the x-axis. I'm going to extend this dotted line out, and I'm going to try to make it parallel to the green vector that I have there. So, it may not be perfect, but this is going to form us a parallelogram here. Okay, our resultant vector goes from the endpoint to the intersection on the other side there. That's kind of ugly. Actually, I'm going to do one thing first before we even draw that in. All right, I'm going to get rid of that. If you've already drawn it, that's perfectly fine. But notice, as I drew that in, it split this 50-degree angle in half, which means I don't have any angles that I know in the, or doesn't split it in half perfectly. It splits it, but we don't know in what proportion. So I don't know any angles. So before I even draw that, in this parallelogram, it is possible for me to find all of the angles of this parallelogram, right? I would know that this angle right here, here. Try this again. This angle right here would be 50 degrees also, because those opposite angles are going to be congruent to each other. So what would these two angles be? Any ideas? Anybody know what the angles of a parallelogram add up to, or anything with four sides? Okay, they're going to add up to a 360 total. So for that to happen, you would have to have this right here would be 130 degrees, and this would be also 130 degrees. So especially when you're not dealing with a, if you're dealing with a rectangle, it's pretty easy to see your angles there. But if you're not, you might want to do this before. You also can just know that the consecutive angles in a parallelogram, the two that are not opposite each other, but the two that are beside of each other, they should add up to 180 degrees. So this, if this is 50, this side, this one right here would be 130. So I'm going to draw in now my resultant vector that I drew in a second ago, but it was like that. And so I need to find the magnitude and direction of this red vector that I have just drawn in. So the magnitude is its length, or represented by its length. Sometimes it might be the force or the speed or something, but it's represented by the length. And then the direction would be this angle right here. I'm going to call it theta. So what we want to do here is we really want to look at this triangle right here, right? Or you could look at the other half, it's fine, but I want the angle right here with one side, what we call a terminal angle, where we've got one side is the 0 degree side, so it would be better to look at that bottom triangle here. So I know this side, I know this angle. I don't know this side, but I could find it very easily. What should this side right here be? It's going to be 4, because it's going to be the same as the one across from it. So this side right here would be 4 centimeters. So in this triangle, I have two sides, and I have the angle in between. What could I use to solve for the x of this triangle? Law of cosines. So I can say x squared equals 3 squared plus 4 squared minus 2 times 3 times 4 cosine of 130. And so you can see why we needed that 130 angle right there. We wouldn't have an angle otherwise. So 3 squared plus 16 minus 2 times 3 times 4 is 24, cosine 130. We'll get x squared equals 40.426. And how do we get rid of that square there? Square root. Let's use the answer feature here. And we're going to get 6.358. So that would be centimeters. That's the length of our side. That seems reasonable because it's a lot longer than the sides 3 and 4 there. All right, so that gives us our magnitude. Of the triangle. Now we need to also find the direction of that resultant vector. So any ideas? What can we do to set up to find the angle? we now have all of the sides, right? And we know one of these angles. So if you have all of the sides and at least one angle, you can use law of sines at this point. I guess you could also set up law of cosines if you prefer it. But I think I'll do law of sine. So I will have sine of 130 over the side that we just found, 6.358. Equals, and we'll have sine of theta over 4. We will cross multiply, so 6.358 sine theta equals 4 sine 130. We will divide by 6.358. So, we'll type that in, 4 sine 130 divided by this answer is going to give us 0.4819. And then we will do inverse sine of that value. And so we get an angle of 28.811 degrees. That is our direction. Now, most of the problems that you'll see whenever we get to test time are probably only going to ask you for one of those because it'll be online, so you only type in one number. So make sure you know magnitude is your length. It's represented by your length of your side. And direction should always have something to do with an angle. Okay, questions on that? All right, let's do one more. I think it's the last one, isn't it? No. Oh, it's the last big one. The very last one there's kind of super easy, but a little tricky. All right, so an airplane is flying due west at a velocity of 120 meters per second. The wind is blowing 20 degrees north of west at 15 meters per second. What is the magnitude and direction of the plane's resultant velocity? All right, so certainly if you're flying an airplane, this is an issue because in 15 meters per second, well, these are meters per second, so they're faster than miles per hour. But certainly, winds make a lot of difference in air travel, right? If you have the wind behind you, you can go a lot faster. If you have the wind in front of you, you're going to slow down. If you have the wind cutting across, it's going to throw you off course, so you would have to adjust based on that. So this is very important. Now, pilots are probably not up there making these calculations, but certainly the instruments that they use would take these things into account. So an airplane is flying due west at a velocity of 120 meters per second. So we're doing, let's see, we got west and north of west. So I'm going to draw mostly the second quadrant here. So north, west. So that one right there is just 2. Let me try this again. It's too crooked. Try to get that west a little straighter there. It's a little better. Okay, so airplane west at 120 meters per second. So that speed is going to be my magnitude. I'm going to represent it by the length of that vector. So I want to make it fairly long. The wind is blowing 20 degrees north of west at 15 meters per second. So north of west would mean that west is the side that we're going to actually touch right here. And we would be going 20 degrees to the north of that. I'm going to draw this as a short vector here because it's only 15 meters per second. And I would label this angle right here 20 degrees. Okay, so we need to draw ourselves a parallelogram here. I'm going to use those dotted lines again. So one dotted line parallel to the blue vector, another one parallel to my green vector here. It's close anyway. And so I will draw the resultant vector. Actually, before I do resultant vector, I'm probably going to need these angles right here. What would this obtuse angle right here be? It's going to be 160 right here. And I know that because in a parallelogram, the consecutive angles is what we call them. The two that are beside of each other, not across from each other, they add up to 180. So 180 minus 20 will give me 160 right here. And so we'll draw in this vector. And so we need the magnitude and direction of the plane's resultant velocity. So magnitude, I'm going to label that there with an X. My angle is going to be this teeny tiny little angle right here. So if this side is 15, we would also know this side over here would also be 15. We are going to look at, you can look at either triangle, but I would suggest looking at this bottom triangle because it will give you the angle right there next to west. It's actually touching west right away. You won't have to do any calculations past that. So we need to set up to find X first. Grace, how can we set up to find our X here? What? Okay. Can we use regular trig on this one? We use like sine, cosine, and tangent. I cannot. Why can I not use sine, cosine, and tangent? It's also 160. But even if I had it, I still couldn't use just regular sine, cosine, and tangent. Connor, why can we not use sine, cosine, and tangent? It's not a right triangle. You can only use sine, cosine, tangent when you have a right triangle. So, in this case, that means we got to use law of sines or cosines. So, if you're looking at something that's not a right triangle, you got to use law of sines and cosines. We've got these two sides right here, and we've got the angle in between them. So, for these two sides and then the angle in between them, we would be using the law of cosines. So to set that up, we would say x squared equals, and our sides here are 15 and 120. So we'll do 15 squared plus 120 squared minus 2 times 15 times 120 cosine of 160 And that is going to give us 18,000-ish here. And then we will square root both sides to get that magnitude, which will be 134.193. And this is our length, so we're measuring it in meters per second. So if you run into this wind, because it's going mostly in the direction that you are, it is increasing your speed, right? So your speed is going from 120 to 134.193. And it asks for magnitude and direction, so we also need to find direction. We need to find this angle right here. Maddox, how can we set up to find the angle that's missing right here? We're going to do law of sines. Very good. How would we set it up? Yep. Very good. And so we'll just cross multiply here. 134.193 sine of theta equals 15 sine 160. We'll divide by this number. And so we will get sine of theta equals 0.0382, and then we will do inverse sine of that answer to get 2.191 degrees. And whenever the problem gives you like north of west, west of south, whatever that it gives you at the beginning, you need to make sure you put that with your answer. So 2.191, that's this little tiny sliver of an angle right here. How would we describe it in terms of directions? What do you think, Noel? How would we describe that? Is it going to be, basically, it's either going to be north of west or west of north. Which one will it be here? North of west. Good. So north of west here. Because it actually touches west. West is the main direction that that angle touches, and you're going to the north of that. Now, if you're doing these problems and you find 2.191 degrees north of west, which I feel like is the most likely way most people would solve this, but your answer choice ends up not being there, always check. If I do 90 minus that answer, it is possible that it would be harder on this problem. I don't think most people would. It is possible that you might see 87.809 degrees west of north. All right, so that would be given like this angle here as 87.809. So if you find that your answer choice is not there, check and see if that might be the case. Typically, I like to give whatever this is smaller angle of the two. So typically, like on answer choices, I usually would not make that the answer. But there's no rule saying that you have to choose the smallest. So it could be okay. All right, we've got one more, and it's not going to take us very long. So vector A has a magnitude of 3 feet and a direction of 20 degrees. Vector B has a magnitude of 10 feet and a direction of 200 degrees. Find the magnitude and direction of A plus B. So if we have our axis here, vector A is going to have an angle of 20 degrees and a length of 10. And we're going to label this angle right here 20. Oh, sorry, I'm reading it backwards. Let's shorten that up a little bit here. Our other vector has a direction of 200. So remember, 0 degrees is right here. Then this would be 90 degrees. This would be 180 degrees. This would be 270. You could go back to 360 here. So 180 degrees is right here, opposite our 0 degrees. Oh, excuse me. We need to go 20 degrees past that. So to draw our second vector, we need to go 20 degrees past that, like so. This angle right here will be 20 degrees. And this vector will have a, this is feet, not centimeters, 10 feet. Now, 20 degrees and 200 degrees are opposite directions, right? There's 180 degrees between them, meaning that they make a straight line. So these are going to be in opposite directions. So if you have two angles that are 180 degrees apart, so if you subtract the two and you get 180, they're opposite each other. So can we draw a triangle for this? That would be impossible for us to do, right? Because it's a straight line. We can't connect endpoints. We can't make a parallelogram. We just have opposite forces here. This would be like some, a plane flying north and a wind blowing south, right? So they're just opposite each other. So when this happens, this is like a game of tug of war, right? If I had a tug of war right here and we put two of you up against each other, right? Your forces are going in the opposite direction. So whoever's force is greater is going to win. They're going to pull the other person in that direction. So direction is just going to go in the same direction as whichever force is greater. So in this case, it would be the 200 degrees because our angle here, right here, that would be the 200 degree angle. So our angle would be 200 degrees. And to find the magnitude, we just subtract. So 10 minus 3 would give us 7 feet. So if we did like a tug of war example here, if I put, I don't know, maybe like Braden up against Reese, they seem to be fairly, I would estimate fairly evenly matched, at least about the same size. Maybe one's stronger than the other, I don't know. So they might have, if they had exactly the same force, they'd just stay in one place, right? They wouldn't move at all. But whoever wins would be a little bit stronger there. Whereas if I put like Caitlin up against Blaine, I'm not sure, but I would imagine, or at least hope, that Blaine could probably beat Caitlin in a game of tug of war. Could be wrong. but physics tells me probably, even though I tell you weight matters a lot for tug of war. The big man has the major advantage in tug of war. Whenever we were in high school, my husband in high school probably weighed about 135 pounds. He was super skinny. And my cousin Megan, she was clocking in well over 200. I'm not exactly sure how much she weighed, but she's a big girl. And so my husband decided, well, he wasn't my husband at the time. He decided that he could beat her in a game of tug of war. So we had a match. For some reason, we had tug of war rope. We had used it for something at school. Anyway, it was at the house. So they were going to have this match of tug of war. Because my husband was definitely stronger than my cousin Megan. Like, he could bench press more. He could, like, they were, he was definitely stronger. He would probably beat her at arm wrestling. But weight matters a lot whenever you're in tug of war. Remember this, those of you skinny guys who think you can beat a bigger girl. Because she drug him across the front yard like it wasn't even, his legs were locked out and he was just sliding across the front yard. So watch out. This is important for you to know. But this is a tug of war situation. All right, so this is not what we are going to do because I have a different worksheet. I've changed what we're going to do here. So let me give you the worksheet and I'll tell you which ones we're going to do. Have an extra for anybody. So we're not going to do all of these. All right, so I do want you to do 1 through 6. 6, it just wants a sketch of the resultant vector. So you could just make your dotted lines to make your parallelogram and draw your resultant vector. So you don't have to actually calculate anything there. I don't like the pictures on 7 through 9, so I'm going to skip them. We're going to do 10. And 12. I'll write these down to you in a second. I need to do one of those. Let's do 15 and 16. I don't love the pictures on 13 and 14 is the reason I'm not assigning those two. I mean, it can be done that way. I usually would draw these, like if I was drawing the picture for 13, because 15, 16, 17, they're the same type of problem. You got two forces with a magnitude of 20 pounds and 14 pounds and an angle of 55 degrees between them. I would draw, you've got your figure here. I would draw, your 14. It doesn't matter which side you put them on. 14 pounds, and 20 pounds. And then I would put that angle right there between them at 55 degrees. So I would draw them so that they're already sort of set up for making your parallelogram. Your resultant is here. That's number 13, but we're going to do 15 and 16 because they don't have the pictures drawn for them. Let's do number 23. And that'll be it. So I'll write those down so you got. I want you to do 1 through 6, 10, 12, 15, 16, and 23. Right here. So you got about 15 minutes. Go ahead and get started on that. I'll be around if you have any questions.